Okay, let's do a little bit of introduction here to chapter 4, some basic graph theory ideas. I don't think you'll find this to be particularly difficult material. It's just you've got a lot of new vocabulary to learn, and let's get on with it here. Okay, a graph, G, is a pair of finite sets, V and E. We're going to call the first set vertices or nodes. The second set, E, will be called edges or arcs. So that each element of E, each edge in E is associated with a pair of vertices, V and W. So graphically, it would look something like this. This we would call the edge E. Now, you can represent this E as a set V comma W. And you know, of course, with the sets, the order doesn't matter. So you could call it the subset WV. And you would say that E is an edge between V and W. You could also say that E is incident. Okay, and you can't read that. INCE, incident with V and W. Or you would say that E joins V and W, and these all say the same thing. All mean the same here. Okay. And also in this case, we would say that V and W are adjacent, okay, because there's an edge joining the two of them. And you could perhaps even say they are incident on E. Okay, an edge that joins a vertex to itself is called a loop. So let's call this guy E1 over here. Okay, so E2 is a loop. This looks a little strange to write it that way, but that's how you would write it. This is not exactly a subset, but it's the edge that joins W to itself. And if more than one edge joins two vertices, so if we had, say had another edge here, then we would call this a multigraph. So more than one edge joining two vertices. And this would be called a multiple edge here. Okay. To kind of sort some of this stuff out here. Whoa. Now, a graph is called simple if we have no loops and no multiple edges. Okay. Now down here I have a simple graph, okay, and the set of vertices is 1, 2, 3, 4, and 5, and the set of edges is, well, there's an edge between 1 and 2, so I'll write that 1, comma 2. There's an edge between 1 and 4, 1, comma 4. There's an edge between 2 and 5. Okay, there's an edge between 2 and 1, but I've already counted that here. Let's see, we have an edge between, let's see, 5 and 3. We have an edge between 5 and 4. an edge between 4 and 3. 4, 5, 6, and I believe that's everything. Okay. Now, so this is a simple graph here. No multiple edges, no loops. Also, take a look at vertex 2 and vertex 3. We would say that those are not adjacent. Okay, so these two guys aren't, because there is no edge joining them. They're next to each other on the picture, but they're not next to each other in the graph. Okay. Now, if we had numbers associated to these edges, we would have what's called a weighted graph. And probably the most common one of those here is, well, here's a road map. Okay. We have real numbers. Each edge. And I've got, these are two different sorts of real numbers here. Is this weighted by distance in this case, and it's also weighted by time. Okay, some things are farther away, but not necessarily take you that long to get there. Okay, so this will be a weighted graph, or it could also be called a network. Okay. Now, a directed graph is it's a graph, sort of. It's a set, you have finite sets, V and E. V are the vertices, and E are the directed edges, where an ordered pair, E here, this is not a set VW, this is an ordered pair. VW means that edge goes from V to W. So in this case, E would be, let me see if I can do a better job of that. Think of it as an arrow. Repeat it up. Okay. Okay, an ordered graph can be weighted. Okay. So we could have one-way streets and so on that have distances attached to them. Let's take a look at this. I've taken the previous set of vertices and put in some directions on some edges. So in this particular graph down here, set of vertices is still 1, 2, 3, 4, and 5. But by putting directions on these edges, and I've actually added an extra edge here, the edges here are an order matters. 1 goes to 2, 2 goes to 5. Okay, we have a 5 goes to 3. We have a 3 goes to 5. We have a 4 goes to 5, and a 4 goes to 1. 5, 6. Didn't do 3 goes, oops, I left 1 out. So 4 goes to 1. Oops. Pardon me, I'm in the middle of making a mess here. 4 goes to 1, and I did it again. And 3 goes to 4. So we have 7 directed edges there. Now, a graph could have, the underlying graph, when you've got a digraph here, a directed graph, the underlying graph in this case would just be the original graph we had over here that had no direction associated with it. If there's a directed edge between two vertices, then in the underlying graph, there will just be an ordinary edge between two vertices. Okay. Now, a graph can have directed and undirected edges on there. We won't really work with mixed graphs. If we have something like a two-way street, then what we'll consider it, there'll be one edge from 5 to 3 and another edge from 3 to 5, rather than a two-way edge between 5 and 3. Okay. Next idea on graphs is what's called a bipartite graph. If if the vertices can be separated into two disjoint sets, let's call them V and W, where each edge joins a vertex of V with a vertex of W. Okay, then this is called a bipartite graph. Okay. So for example, I'm going to take a graph here. My one vertex set is going to be ABC. Another vertex set will be XY. Okay. Okay. So here's A, here's B, here's C, here's X, and here's Y. Okay. So I'll have an edge between A and B. Let's have an edge between B and X, an edge between B and Y, one between C and X, and one between C and Y. Okay. So our edge sets will be AX, BX, BY, CX, CY. Okay, this is a bipartite graph here. You can generally arrange them to where they look something like what I've got drawn here. Excuse me. Now, a complete graph. Okay, a complete graph is a simple graph, so no loop and no multiple edges. Okay, where every vertex, excuse me, I don't want to quite, I'm getting ready to say it poorly, where every spell things right, where every pair of vertices are joined by an edge. Okay, let's suppose we have, say, 4 vertices here. A, I don't need to circle around it. A, B, C, and D. Okay, so if they're joined here, A is joined to B, A is joined to D, A is joined to C. Okay, C is joined to B, C is joined to A, got that. C is joined to D. Okay, B is joined to A, I've got that. B is joined to C, and B is joined to D. This has a name here. This is what's called K4, sub 4. This is the complete graph on 4 vertices. Okay, so we would use, for in general terms here, K sub n is a complete graph on n vertices. Okay, so what would that look like? So here's a question for you, and it's one of the homework questions. How many edges would something like this have? While we're thinking about this, we can combine these two ideas to a complete bipartite graph. A bipartite graph is complete, well, if there's an edge between every vertex in V and every vertex in W. Okay, so let's go back to this. This one I have up here is not complete, okay, because I don't have an edge between A and Y. Let's do another one here. Let's put A, B, C, D, and Y, Z here. Okay, so if it's complete, then everybody on the left is joined to everybody on the right. A is connected to Y and to Z. A lot easier said than done working on this thing here. Okay. B is connected to Y. B is connected to Z. Make big dots here where they're connected. C is connected to Y. C is connected to Z. And D is connected to Y. And D is connected to Z. This guy has a name. K, we have 4 elements of one set of vertices and 2 of the other. So this is K42. It's the complete bipartite graph on from a set of 4 vertices to a set of 2 vertices. Okay, so next question. I think this is a question in the homework. Okay. How many vertices are there in the complete bipartite graph KPQ? Okay, so P number of vertices in one set and Q number in the other. Okay, going on here. A graph G prime, which we'll say has a vertex set V prime and edge set E prime, is a subgraph of a graph G if V prime is a subset of V and E prime is a subset of E. Now, since a G prime is a graph in its own right, the edges in E prime must correspond to vertices that are in V prime. There's a particular type of subgraph here. Okay, so let me do an example. Scoot this guy down a little bit out of the way here. I'm going to draw a graph here. Let's see. Let's put A, B, C, D, and E. And let's try these guys here. A to B, stay in there now. B to C, C to D, B to D, A to D, A and E, E and D, and E and C. Okay. All right, so in this case, I have V to be the set A, B, C, D, and E. Now, if we take a subset of V, and let's just take the subset that's A, B, D, and E. Okay. Okay. What this does is this induces a subgraph. Okay. Okay, the subgraph induced by W is going to have A, B, D, and E. A will be connected to B, B will be connected to D, D to E, E to A, and A to D. Okay, so this is the subgraph that's induced by the subset of vertices. Okay, now graph theory is an idea that got its start looking at a town in Prussia called Königsberg back in about 1736. And the book describes this as well, but I put a little link there to a talk about the Königsberg Bridge problem. And we'll talk about that in much more detail in a later lesson. But here you go. This should get you started on chapter 4, and you should be able to work the problems in the homework without too much difficulty.